Salam sejahtera and good morning. My name is Lawrence and I am from MIMOS Berhad. MIMOS is an agency under the Ministry of Science, Technology and Innovation. I'll be your host for today's webinar. Today we'll look at advanced analytical services. As all of us are well aware, we are in the midst of a global pandemic. Let's do our part to fight this. Get your vaccine and follow the guidance of Kementerian Kesihatan Malaysia. During our webinar, please make sure you mute your microphone. Should you have any question for the presenters, you may use the chat box available in this app. The presenters will address your questions right at the end of all presentation. Our first speaker is Dr. Jasmine Kaur Sarjit Singh. She will bring us up to speed on MIMOS Semiconductor One-Stop Advanced Analytical Shared Service Center for Failure Analysis and Material Analysis. Dr. Jasmine Kaur has more than 8 years of experience in material characterization, especially in nanotechnology. She obtained her PhD majoring in advanced material and characterization from Malaysia Japan International Institute of Technology, University Technology Malaysia. She received hands-on training from Kyushu University, Japan for advanced method of high-end microscopes. Currently, she is a senior engineer at MIMOS and technical expert for transmission electron microscope equipment. Now, without further ado, I'll hand over our webinar to Dr. Jasmine. Over to you, Dr. Jasmine. Please take control. Please unmute your mic.
All right. Thank you so much, Lawrence. A very good morning to everyone. Thank you so much for joining us today, despite your busy schedule. And as you know, with this pandemic, many of us are going through. We are trying our best to strive hard to do what we can. All right. May I get someone to mute the mic? All right, so we do have two campuses, as some of you know. One is in the northern region, a branch which is at Kulim High Tech Park, and the central region is at Technology Park Malaysia at Bukit Jalil. So we are very close by the Bukit Jalil Stadium. All right, so we play the role as government agency which support the national interest by providing the infrastructure to the country. And through us, local companies, actually, you can enjoy the competitive rates in terms of analytical services and equipment. So which would otherwise you have to go and source it out overseas. And due to that, you have to pay higher prices due to the exchange rate. So by making our service available in Malaysia, we can support the government initiative in sustaining foreign investment in our country. So with the existence of MIMOS for more than 20 years now, we have actually grown to become an entity similar to other world-class institutes such as A-Star Singapore, E3 Taiwan, and KIST Korea, and IMEC in Belgium. All right, so we are accredited with ISO 17025, which acknowledge the competency and validity of our testing and calibration results nationally and internationally. For example, E3 Taiwan has validated our measurement process through interlab measurement comparison for the use for the Taiwanese Nanotechnology Industry Development Association, TANIDA. So we have actually fulfilled the requirement of ISO 17025 for measurement for micro and nano level scale, nanoscale level, which means our lab meets both the technical competency as well as the management system requirements that are necessary for us to consistently give a valid test results and calibration and calibration, and our verdict is valid in the court. Okay. So moving on to the next slide. Okay, this is the failure analysis lab personnel. So every equipment is designated with a personnel which has more than 20 I mean, they have more than 20 years of experience in this FA analysis. So you can, I mean, rely on our results, and they have very high skills and so on. All right, so what is failure analysis? Failure analysis, as you know, is a systematic diagnostic process to identify the root cause of a design or a product failure or a wafer or package. So our job is similar to a doctor's daily work. Instead, they are diagnosing human. We are going to diagnose the failure of the product. So example, the equipments which are in the hospital are also similar to what we have in our lab. For instance, we do have the 3D X-ray, ultrasound, and various kind of microscopes which can magnify from 10 times up to 1 million times. All right. So let me just try this cursor. All right. So example, we do support the E&E value chain. For example, if you do have some manufacturing issues for the industry, especially, so what would happen is the productivity will come down, and then there are a lot of scraps and things like that. So that is where they need our support, all right, to identify the type of failure, the root cause of the failure. So we do, these are the type of example of analysis that we carried out here, and then to identify what type of failure and so on. And then from there, we provide a report. So it's based on data driven, so that the industry can further have improvement and correction to their particular failure. And then with this, it can increase the productivity and reduce their cost for any scrap and so on. All right. So what is needed? What is needed for successful failure analysis? So three things. Firstly is the process flow according to the industrial practice. Secondly is the right tool for the job. So it's very, very essential to have the right tool for the job. So if in case you are unsure that which analysis you're supposed to do, sometimes you're just reading from the literature or you've seen some other examples, you can always consult us, and we do have the in-house experts which can give you some consultation on which is the right tool you can use for your particular job, because we do have the network and shared facilities. And if in example, if we do not have that particular equipment, we can channel you, or we can guide you to our partner lab. We have the partner lab concept where we will introduce you to the partner lab. Then from there, what they call, you can get the information and so on. All right. And lastly, the skill and experience I mentioned just now. We have more than 20 years of experience in failure analysis and good networking as well. So let me go through the scope of presentation. So I'll be talking on the importance of FA, and then the general process flow. Most of you, if I've seen some of you are from the industry, you would be very, very familiar with this process flow. But so that's why I will go through very generally, and then in detail, if you have any questions, you can ask in the end of this session, right? All right, so basically 2 categories of characterization technique. Firstly, the microscopy, and secondly is the spectroscopy. So we'll go through this. So if there is a suspected failure, the first step is to do the verification via the curve tracer, and then we do the non-destructive inspection, package opening, followed by electrical fault isolation. Then we go on to the physical analysis, and some of you just want to stop at the physical analysis if you have enough information, but some also require to go up to the material analysis. All right. So this is the example of the electrical verification, whereby you can, the CRT, it shows, the screen shows the behavior of the current when voltage is varied. So you can identify whether it's a leakage, a short, or whether it's open. And then for non-destructive tests, we have the 3D X-ray. All right. So as I mentioned, like hospital, you can see the type of failure there, whether it's a lifted wire or voids. And we also do have the scanning acoustic microscope to identify delamination. So these are the non-destructive tests. So it doesn't destruct your sample at all. And then for the package opening, we have laser decapsulation and chemical decapsulation. So for electrical fault localization, you have to identify whether it's a leakage characteristics or a short characteristics. So for the leakage one, we can use the photon emission microscope. So that is the example of a good and a bad image, as well as for the thermal emission microscope, you have the short characteristics. You can check the good and the bad image as shown in the example here. Okay, for the failure analysis tool, as I mentioned the term, under microscopy, it's a technical field where you use various kind of microscope to view samples which you can't see in with your naked eye. Okay, so under this we do have the Fib Sem, which is called the dual beam, whereby the focus ion beam is incorporated together with the scanning electron microscope. So basically you can do the milling of the sample as well as you can view it together. So this is a sample preparation method also before we can view under the transmission electron microscope. This is our Fib SEM. So they have incorporated with the Fib and also the SEM. So in order for us to view the sample under the TEM, this is essential to either, go through the Fib SEM. These are mostly for samples which are like those thin films and maybe LED. So we do get a lot of what they call requests on this. And for other than another sample preparation, which I didn't include here, we do have a cryo ultra microtome as well. So those samples like rubber, they are too soft to, hold it directly, or we can't view it directly in the TEM. We can actually prepare it by doing the slicing process manually and then slice it below 100 nanometers so that we can view it under the TEM. And there's AFM as well. All right. So this is the difference between a SEM, scanning electron microscope, and a TEM, transmission electron microscope. So for SEM, the electron beam would, what they call, it will only give the specimen surface information because the electron beam doesn't transmit through the sample. It just do the scanning at the top part of the sample. So you only can get topography information on the surface. Whereas the TEM, you can observe the inner structure because the beam will penetrate to the sample and you get more information. And we can actually, sorry, okay. So this is the example. So we can actually zoom it further to get the inner structure. You can see the what they call you can get better information, and we can go up to nano levels. So our equipment is has the capability to go up to 1 million times. All right. So what are the information, the techniques that we use is to get the morphology of nanoparticles, and then what are the defect in nano size, so we can further see it. Sometimes in Fib SEM, we can't really magnify further. Maybe I'll show you the example later. So you can't see the defect clearly, but then in TEM, you can actually identify and see the defect clearly. And then we can also identify whether the what they call the sample, is it polycrystalline, amorphous material, by doing the SAED technique, by using that. And then also some customers require to measure the thickness of your thin layers. Particle size measurements, okay, we are working together with Nano Verify to verify the nano size, what they call particle measurement, whereby companies, they claim that they have added nanomaterials in their products. So this is where we actually help the Nano Verify to confirm the claim, and then to make sure that we have measured like the particles supposed to be in nano size between 1 to 100 nanometer. And yeah, so we do get a lot of requests from various companies, and products such as like sanitizers at these days are getting really popular. And then we do have sanitizers, we do have like soy sauce and nano sugar, and so every products, nowadays they are using nano materials to enhance their properties. All right. And last but not least, the lattice spacing measurement as well can be done via this. All right. So as I mentioned just now, we can't get a clear, like as you can see, there is an abnormality in the Fib Sem image, but then you can see it, the overview by using by TEM, and then we actually magnify it further. So you can actually go up to the very high magnification and you get a very clear image of your abnormalities, and we can also measure it, and then some of them require to know what is the element present here at this particular abnormality. So whether it's a copper migration on your sample or whether you want to identify it. So we do the EDS mapping. I'll explain further. Okay, so what further information can we obtain for determining the failure? So microscopy has its own limits because you can't identify what are the elements that. All right, so when we move on further, what do we need? So we do need to use the spectroscopy. So this is where the spectroscopy comes in place. So we hand over the task to spectroscopy-based analytical equipment. All right. And then, so spectroscopy basically is to reveal the chemical composition, the composition variation, the crystal structure and photoelectric properties of the material. So in this, we do have TOF SIMS, AES, as well as XPS under spectroscopy. All right, so it's a branch of science that deals with the study of interaction of matter with light through the electromagnetic waves. To complement that, we do have the FTIR, which our expert is here today. They will be telling us more on that, as well as UVVs. Right. So these are the type of spectrum which you can obtain from this particular analysis. So what is the difference between a bulk versus a surface analysis? So sometimes you want to see in bulk, example, it doesn't matter, your element is, you want to identify the element at the whole bulk surface, I mean the whole sample. But some of you have done like the growth of the thin films, like, only at the top surface. Maybe you have grown some aluminium on the top, which is less than 3 nanometer, and you want to identify it. So which is the proper equipment which you need to use? So you can't use the normal EDS because in bulk you will get, if you're using the bulk surface analysis, bulk analysis, you will get the whole region. You're not only getting at the top on the near surface. All right. So this is where we have different kind of probe size. For example, the types of under OJ electron spectroscopy, the AES, they're using the source is electron. So the probe size is about 20 nanometer and the depth of the penetration is about 6 nanometer. So you can get information up to 6 nanometer. Same goes to XPS, but the depth is higher, about 10 micrometer, and they're using X-ray source. And for TOF SIMS, we're using ion source with 100 nanometer depth. The probe size with 1 nanometer depth. So it's very, very shallow. Okay. And then for this, what are the elements which we can detect is for AES is from lithium to uranium for AES and XPS in a part per million. Whereas for TOF SIMS, we can detect starting from hydrogen to uranium from part per million to part per billion, right? And this is the type of mapping which we can obtain from this particular equipments as well, right? So as I mentioned just now, EDS detector is actually, it's already attached to the high resolution TEM, Fib Sem and dual beam. All right. What are the signal what are the information you need? For example, the EDS spot analysis. You need to know at that particular spot, what is the element present there? So you can use the EDS spot analysis. And then sometimes there are customers who wants to know along the thin film, they have a few layers, right? So they use the line scan analysis to get the further information together, so we can give the line scan to show that this element is present at this particular layer. And then EDS mapping analysis basically is for failure. Example, like if you want to do the mapping in terms of the concentration of the elements. So we give you like it comes out in colors, so you can identify where is the, as I said just now, the abnormalities is it has copper on it. So it will give a very nice mapping showing that there is copper present and what are the other elements as well. So for FTIR, Fourier Transform Infrared Spectroscopy, so if there is a suspected material on the contaminated sample, so we would actually match the spectrum and then to identify that the suspected material is on the contaminated sample, okay? And then in situation whereby the microscopy and EDX data is not sufficient, so you feel I still need to, identify what is this specimen. I'm not happy with what I've got. So you can use the FTIR spectrum matching, and then the technique, the complementary techniques are FTIR. So if we don't have the suspected material, you can actually, we would actually get it from the library, whereby when we do the spectrum matching, you can get the particular information. All right. So these are the range of failure analysis, what they call equipments that we have break it down into the electrical lab, under the physical lab, as well as the material lab. So these are all the equipment. And for the capabilities, yeah, you need to have, sometimes we get requests from customers which they're not sure. Okay, when I send my samples, I need to prepare it, example, like what size it's supposed to be so that it can directly go into the equipment, something like that, right? So basically you can, we can assist you in that. And then what are the types of analysis that certain equipment can do, whether you want to check for your analysis is organic sample, inorganic sample, the type of analysis for elemental, do you want to do imaging, do you want to do mapping, and so on. So these are the information that we can give it to you, right? All right, so that's about it. I didn't take much of your time. So if you do have any questions or any further inquiries, you can always email us, and we would be very happy to, get back to you. And we would, we do have a list of our, I think I can see some of you, our like existing customers. Thank you very much for your support here. And you have been always supporting, and hope we can collaborate further. And our new upcoming potential customers who doesn't know much about MIMOS, we welcome you to always, write an email to us. You can go to our website, you can call us, and we would be happy to assist you in any way that we could. Okay, thank you very much for your time. And yeah, I hand it over to you, Lawrence. I can't hear you, Lawrence.
Thank you, Dr. Jasmine. It's very in-depth information about what MIMOS does and what you've been doing for customers. Thank you very much. Our next presenter is Ms. Chow Mei Ling. Ms. Mei Ling graduated with Masters of Philosophy in Chemistry in the University of Malaya. Currently, she is the spectroscopy product specialist in Agilent Technologies Malaysia Sdn Berhad. She's also a technical expert for molecular and atomic spectroscopy solution implementation. With that short introduction, over to you, Ms. Mei Ling. Go ahead, Ms. Mei Ling.
Okay, good morning, everybody. So my name is Mei Ling. So I'm the Agilent Spectroscopy product specialist based in KL. So basically, I take care of two range of product. One is the heavy metal atomic, example like ICP-MS, ICP-OES. The other one is molecular product, like today what I present, FTIR, UVB, fluorescent, and Raman. Yeah. Okay, today's topic is about the fast and automated microplastic particle analysis. So I'm not very sure about how the audience here understand about microplastic, but I believe that everybody heard this word, okay? Or unless you heard something plastic. but how small is the plastic here? So this is today's discussion over here. Okay, so this is basically the definition. So the microplastic issue does not really need introduction. I believe that everybody heard more or less about it. Okay, the public awareness on microplastic are an emerged pollutant is massive, especially today. A lot of things because of the pandemic, we use of a lot of plastic material, Tupperware, our masks, our disposal, packaging, everything, yeah. So risk and impact associated with the microplastic. So small plastic can translocate and up inside the tissue of organisms. So the smaller the particles, the higher the risk. So the microplastic can be a vector, that means it's as a carrier for pollutants that are part of the plastic. Example, the plasticizer, flame retardants, metals, biocides. Okay, so the microplastic can act as a solvent as well for pollutants and hereby act as a vector. So same thing here, the smaller the particles, so the higher the risk. So until now, the practical analytical technique for very small particle analysis means that less than 50 micrometer or even less than 10, so have not been available. So it will be a very tough analysis. So which is important, it is these small particles that are most biological and toxicological relevant. Okay. Okay, so plastic also have a different type of plastic. So for us, maybe we think that everything is under plastic category, but actually if you want to categorize it, so we have a different type of plastic. So like example here, we can classify the plastic as PETE, HDPE, okay, or the most common, the PP, PS, or PE type. So, and of course, one more thing that we always forgot is rubber. So is it rubber as a plastic as well? So if you look at here, actually the rubber also come into a lot of type. Okay. So other type of plastic less often thought about is paint. So have you ever think that paint also part of the plastic? Okay, so there are also copolymer. That means there where the two or more different monomers unite and polymerize together. So the common example like are PE, PP copolymer. So there are composite plastic like fiber reinforced plastic or light milk cartons. So if you look at the box, it looks like just a paper box, but actually they have some plastic in it as well, yeah. So that is how we define all these microplastic. So we also talk about the size. So for those big, okay, we call it macroplastic later. So that means anything that you can see with your naked eye, you can trace with your naked eye, we call big size. Okay, but anything that are very small, but actually is present in the sample, we call it microplastic. So normally the range is about 5 mn and down to 1 micrometer. So sizes down to 100 micrometer are visible to the naked eye, but characterizing something as plastic at that size is impossible without the tools. So nanoplastic, that means below 1 micron. Okay, so we also talk about the shape of the microplastic. So more or less spherical particles from example cosmetic plastic beads only constitute a tiny part of the total plastic pollution. So fragments of plastic, for example, defined as length, okay, the width, so less than 3:1 are common. So fibers, for example, defined as length and width, more than 3:1 are also very common. So especially fiber are very difficult to quantify as well, like this. So you need a microscope to look into it and zoom inside to look for this fiber. So think of plastic quantification as a three-dimensional issue. So the size, the shape, and of course the material itself. So, but it gets a bit more complicated because not all that is out there is plastic, because some of them, they have a mixture. That's why maybe you will have a transition thinking, yeah, whether you should classify it as a plastic or you should not, because they are all mixed together. Okay, so and fortunately there is much more other stuff out there than plastic. So I nearly forgot, yeah. So how you want to do this analysis? So you also have to sample the plastic, and sampling depends on which system you sample from. So what size range you target? So do you go for a large particle? That means you can see with your naked eye, or you go with a small one that you cannot see with your naked eye. You need a microscope or imaging system to go into detail and zoom and look for it, yeah. So this is how you want to start before you want to do this microplastic application. This is all the thing you should think. So like example, the size range to target. So the size, how big, how small. So system to investigate. So what is the instrument that you want to use to do this application? So the material to target. So what use you want to make of your data, how you want to reprocess your data. So you want to do quantification, or you just want to do a screening. Okay, so all these parameters are important when you decide on sampling approach. So your sample purification and microplastic extraction. So how you want to do a sampling. So analytical method to quantify the microplastic. So the post-processing of the data, that means after you get all your sample analyzed, how you want to use the software to do the interpretation. So I give you a chart here, basically just to give you a guideline. So what is the size of range that you are talking about? And then what type the instrument should be involved in your analysis. Okay, so if I go to the next slide, so I just give you a very basic summary. So like I just now mentioned before, so if you have a very small 10 to 300, then maybe you need a microscope. You can see the picture here. This is how the instrument look like. So if you can trace the microplastic by your naked eye, big size, more than 300 micron, okay, then you can use the normal FDIR, the bench. So here I will go with those you can see with your naked eye first. Yeah, that means quite big. Basically, the size of the microplastic is quite big. So like I mentioned, you can use the small FDIR, the bench type, to do your analysis. So this Agilent FDIR Carry 630 basically come with the ATR accessory. So the single particles normally we talk about is more than 300 micron. So from the instrument, okay, you can see from here the slide, this is what I mean. You can see with your naked eye. So that means you can pick it up and put on the analyzer and scan. So at the end, you will get the spectra over here. So from the library search, then you can do the identification whether this sample is from PP, PE, or PS. Okay, or it's a core polymer that is a mixture altogether. So people also use this bench FDIR to do returning behavior of people. So in overseas, there are people who do some study how our people throw the rubbish. We call it returning behavior. So basically, this researcher, he will go to the rubbish site and collect and do all the sampling and study the behavior of the people. Okay, so same thing, he will analyze the sample, get the spectra, and then do the identification over here. So the other instrument that you can use is we call the 4500A. So if you do a comparison, what's the difference between this instrument, the Carry 630, compared with this one, the 4500A is, if you look at this picture again, so for this researcher, he have to go and take the sample, okay, and put on the analyzer to scan, okay. So if you compare with this one, it's the same, but this is a portable type. So like example, you want to do a research on the beach side. So it's very tough for you to sampling all the plastic on the beach side and bring back to the lab. So it's not so convenient when it comes to work. So you prefer will bring the instrument to the beach, okay, and do the analysis. That means you collect all the sample, on the spot you do the analysis, and then you start your interpretation. So this is a portable type, okay, it comes with tablets. So you can see how he do this, okay. So this is how the instrument look like. Basically, it's just like a box. So you can just carry the FTIR analyzer and then go to everywhere. So the other one is we call the handheld. So handheld, I mean you can hold the instrument with your hand. That's why we call it handheld. So you can scan the sample as it is. So the previous two, you still have to take the sample and bring to the analyzer. But this one is, okay, whatever sample at that location, you just scan as it is. So you don't touch the condition of the environment. So like example, you have a plastic here. So you just scan, and over here you have a mini iPad. So from this screen, small screen, you can do your interpretation as well. Okay, so this is how you do it. Okay, so basically this research we do was conducted in this South Queensberry, okay, next to this iconic Fort Rail Bridge. Yeah. So this is what you can see from the beach. So you can find those tiny plastic. Okay, come with different color and also the shape. So I just want to share a very interesting research based on this Carry 630. So if you look at here, so how far that the Agilent Carry FTIR 630 can travel. So how far this instrument can travel. So if you are interested, actually you can type it here in your YouTube. Okay, you will get this article. So Earth highest, driest, coldest, and winter's continents remain a dream for many, right? So hard to reach, tough to live in, and a privilege to see with your own eyes. So 5 passionate volunteers, so selected from more than 140,000 applicants, got to experience the vast beauty of the great white continent firsthand as part of the Antarctic sabbatical. So you know where is Antarctic? It's a penguin live, whole place. So what is the purpose of doing this? Actually, they want to investigating whether the microplastic have reached the frozen continents and what impact they have on the planets. So if you are interested in this particular, when you go to this YouTube, actually it's a very interesting. Okay, but I will not share the YouTube here today. Okay, so this is how it look like, the environment. So this is the person in charge. Okay, this is the lab condition. So this is how they do the sampling. So you cannot take the snow, okay, from the surface. So you have to use the tool to dig in at certain depth, and then you collect the samples. So after that, you bring back to the lab, you do some sample pretreatment. Okay, you do some process, you filter, okay, then you put the sample onto the instrument. So from this picture here, you see my baby, carry 630. You spot any of the instrument? Actually, it's here hiding behind. My baby very shy. So it's right here. Very small baby. So why they bring this instrument basically is a very small instrument, okay, but can manage to do the Ftir analysis, and it can stand the condition there. So that's why it's easy for them to bring. Okay, so that's the story. Yeah. So this is microplastic as well, but using the microscope. So this is the system in MIMOS. So they have the bench Fdir. Okay, if you want to do a big size microplastic, so you can use the bench. So if you think you want to go with small size, then you can use the microscope here. So, but before you go to scanning, of course, we talk about the sample pre-treatment, but I would not go into detail. Yeah, actually, I have a video how to do it. Okay, if you are interested, then you come back to me. Yeah. So how you have to pre-treat, it depends not only on your sample, but also on the instrumentation you use to quantify the microplastic. Through such sample preparation step, depend on the complexity of your matrix as well. So we are talking about raw wastewater here. That means your sample basically is a water type. So this is the step, okay, that you have to go through, okay, to get your sample. So there are a lot of people also do on the soil, that means the solid sample. So we also have the step, okay, advise you how you should do your sample pre-treatment also. So beside all this, I believe nowadays, if you go through all the journal paper, there are a lot of people study microplastic in our food also. Like example, in our fish, okay. So this is the apparatus setup. So you have to go through the filtration. So after your filtration, so this is something that the blue one, you can see with your eye. Okay, so all these, it will be on your filter paper. So then you can use the microscope to look at it, okay, and identify it. But there are people also, they don't have microscope. Like I mentioned, if you can see the blue here, so that means actually you can pick it up. Okay, once you pick it up, then you use the normal Fdir to do the scanning as well. So this is another application. So this is exposed to microplastic in indoor air. That means, you know, in your room, you got aircon. Actually, this is more toward the air monitoring. So this is measurement in 3 student labs. So like I mentioned, so you have to buy this, we call the sampling gadget. Okay, so inside it actually there is a very small filter paper. So when you take out the filter paper, okay, you can see a lot of things here. So you will use the microscope to zoom in and get the distribution of all these microplastic, and then you do a scanning and identify. So just give you a very simple idea how the instrument do this work. So basically you can see from here, okay, this is the visible image. Visible image, that means you can see with the normal light of the microscope. So after you see, okay, you want to go into the area that you want to looking at, then you will go to this image. So for the image itself, okay, you can zoom in and you can
Dia bagi banyak gaya.
okay, then it will show you the spectra of the Fdir. So how does it work? So like I mentioned, sample pre-treatment. Okay, this is the first step. So you collect the sample and then deposit a sample on your slide, the microscope slide. window or filter. Then after that, you have to scan it, and then you interpret the scan data. Okay, you can use the library the polymer library to help you to do this identification. So this is basically, so if you still remember the filter paper just now, so this is the distribution. So from here, of course, there are some is microplastic, there are some is not. So you can look into it, okay, one by one and do the spectra. Okay, so what is a good thing about the microscope in MIMOS is they come with the FPA, focal plane array. So this is a technique, the advanced technique, whereby if you have a microscope, so you can one-time scan. Okay, it's just like one snapshot. It's just like a camera. So when you take a picture, you one snapshot, everything in. So this is the same. So under this filter paper, so what I do is I do a one snapshot. So after one snapshot, that means all the image spectra all I capture. Then only after that, I do my data reprocessing. I go into a place. Okay, like example here, then I click on it and then I do the identification. Okay. So the other type of technique which is very popular for today is we call the LDIR. It's a laser direct infrared. So the instrument actually very small. So it did not come with a microscope. Okay, basically how it works is you put your sample in this slide. Okay, and then you insert it. So under the slide, then the thing will just scan. It's just a laser, it will scan and then capture the whole image. Okay, so just now the microscope, you still have to focus if you purchase though a single point. Okay, but this one is more convenient. Yeah, this is more advanced. So same thing here. So you still have to do your sample preparation. Okay, so sample preparation and then you suspend in ethanol and sonicate. So after that, you put a liquid on the slide. So, and then you insert the sample into the instrument. So you locate the particles, you acquire the spectrum, you compare to library, and then you update your statistics. Okay, this is how the software do the job lah. So this is basically the whole workflow. Okay, I can show you how actually it works. So if you look at this video, yeah. So you zoom in. Okay, you're looking at your particles, the microplastic. Okay, then you identify your focus. Then it will scan, like I mentioned, is a laser. It will scan. Okay, so after that, it will come to data processing. Okay, so you will get all this information about the shape of the plastic. Either it's round, triangles, sphericals. Okay, and of course you can get the particle size and you can do the identification. You can get the spectra, you can compare with library. Yeah. See, you can see the spectra here. Okay, then you can go to the next one, this shape. Okay, then it will tell you this shape of microplastic belong to which location over here. Okay, everything will be linked all together. So you can do one by one study as well, yeah. Okay, so just to give you an idea, so like I mentioned, you can see this is the identified as a PS, polystyrene. Okay, so this is how the microplastic look like under the focus. So this is the spectra. So basically you can click one by one and check in detail. They also provide you about the particle size also, yeah. So of course, like I mentioned, normally FTIR come with a library, so for easy identification. So from the previous, so you can see once you identify them, they will tell you that this is PS. So it's about 31 micron. So this is the spectrum. So same thing with the PE, polyethylene, 66 micron. And this is the spectra, how it looks like. So you will get a picture also. Okay. Okay, so that's all from my side. Okay, thank you, everybody. So now go back to Lawrence. Thank you.
Okay, thank you very much, Ms. Mei-Ling, for your presentation and showing us the different equipment that we use to do this analysis. Thank you very much. Okay, our final case study is from Dr. Muhammad Faisal. Dr. Faisal is a senior lecturer, Department of Chemistry, Faculty of Science, University Malaya. Dr. Muhammad Faisal has vast experience in the field of ultrafast femtosecond laser spectroscopy, having worked in this area since 2014. He holds a PhD degree from Nanyang Technology University, Singapore. While working for his degree, he has the opportunity to build up ultrafast transient absorption and multidimensional optical spectroscopy experiment in the School of Physical and Mathematical of Science, NTU. Currently, he holds the post of senior lecturer in the Department of Chemistry, Faculty of Science, and teaches courses related to molecular spectroscopy since 2019. With that introduction, ladies and gentlemen, I hand you over to Dr. Faisal. Over to you, sir. Please take control.
Okay, thank you very much, Lawrence, for the nice introduction. And Assalamualaikum and Salam Sejahtera to all the audience. First of all, I would like to say thank you to the organizer, MIMOS, for holding this webinar. Actually, this is my first time giving talks in industry. So my name is Muhammad Faisal. I am actually I'm actually a senior lecturer in University of Malaya. Okay, I'm working in the Department of Chemistry, Faculty of Science. So a bit about my introduction. Previously, I did my bachelor degree I pursued my PhD in NTU in a field called Ultrafast spectroscopy. So it's a physical chemistry. And then after I did my PhD, I did a short postdoc in Sultan Qaboos University in Oman. I was invited by a professor for 4 months while waiting my official letter to join them. Okay. I just want to share a bit about our department. We have about 53 academic staff led by our head of department, Professor Zanaria. I think we have a very good team over here. They are very expert in their respective field. And we also have a different in chemistry, inorganic analytical chemistry, and physical chemistry. Okay. All right. So you can visit our website if you want to know more about each of the lecturers, probably their own field, or you want to collaborate with them. Okay, now let's go back to the business. So my talk today will be on very fundamental things. You have heard from the previous speakers, more about applications, using instruments. So I'm going good. I mean, as an academic, usually we emphasize on the fundamental because we don't want we don't want to just use instrument like a black box. We want to understand behind the science of the instrument. and science in terms of the chemical and biological samples, right? So in this talk, I will I think the spectroscopy term is not something that's related to industry, and the purpose of this talk is to give a fundamental understanding of molecular spectroscopy as the most important tool in understanding the molecular structure and its characteristics. So personally, I believe that we wouldn't have achieved the advancement in technology that we are seeing today if it is not spectroscopy. And personally, for spectroscopy is the most field, because I give you an analogy. Your spectroscopy is like you enter a dark room and you are given a torchlight, So without a torchlight, you wouldn't be able to see what is inside the dark room. So it's similar like spectroscopy. And let's say if you know about NMR spectroscopy, is to actually characterize what kind of compound you have synthesized, right? So if we don't have NMR spectroscopy, we wouldn't be able to know what type of molecule we have in our test tube or the one that we are synthesizing. Okay, so spectroscopy is very important. So for the next 40 minutes, I'm going to tell you some of the theory. Basically, the definition of spectroscopy is a study of interaction between electromagnetic radiation and matter as a function of frequency or wavelength. Okay, the basic understanding is that we have a light source, a tunable source, and it emits light. Then we direct it to our sample. Okay, and then we have a detector to measure how much light is being absorbed or emitted. Now in spectroscopy, the light source is the most important thing, and we know that light is actually an electromagnetic wave in which its wavelength range from as small as atomic nuclei to as big as a tall building or Statue of Liberty. Okay, so for a certain range of wavelength, we label it as wave, and we have microwave, infrared, and then we have a visible light, the one that we can see by our eyes. It is actually a very small region in the electromagnetic wave. And then the visible is from 380 nanometer to 780 nanometer. Okay, and besides, there are also other ways to represent the electromagnetic wave. Sometimes we use wave number, sometimes we use frequency and electron volt. This is all interchangeable. Light matter interaction. Okay, we need to understand that it follows the quantum mechanical properties, which stated that the energy level of a molecule are quantized, or they have a discrete energy level. They are not continuous. And usually we will visualize it like a line like this, to indicate the ground and excited state. Okay, the lower line will be the ground state, and the upper line will be the excited state. Okay, so for most of the molecule, it will start. The most of the molecule will be in the ground state if there is no light interacting with them. And once we shine it light with a sufficient enough energy, it will excite to the upper state, or we call it as an excited state. Okay, and subsequently they won't stay at the excited state forever because it is relatively unstable. So eventually they will go back by emitting light. Okay, so that's your energy conservation there. And another important condition that is in terms of the population distribution. We need to determine which level are significantly occupied and hence likely to undergo absorption of energy. So if upper and lower energy level are equally populated, then and equally likely, and so no spectroscopic transition will be seen. An example of this is the NMR spectroscopy. So in NMR spectroscopy, the ground state and the excited state are almost equally populated. Okay, because of later I will tell you about the Boltzmann distribution. Then the signal observed will be very, very low. Okay, so when the ground and excited state are almost equally populated, then you need to have a very sensitive instrument to detect the signal. So generally, to record a spectrum, there must be a difference in population of the two states involved. And how to determine this? Let's say we want to measure the population distribution of the two energy level at room temperature. We want to know how much of our molecule at ground state and how much is at the excited state. So there is this equation called Boltzmann distribution function, okay, where you can use it to calculate the population ratio. Okay, you put in the different excited state and the ground state and the temperature, and K here is called the Boltzmann constant. So what will happen if you measure your spectrum at lower temperature? You expect that most of the molecule will be at the ground state than the excited state because of this equation. Okay, so if you have you measure it in cold temperature, then you will see more transition to excited state happen. Okay, and besides the Einstein has said that the rate of absorption of photon is proportional to the density of the electromagnetic field with the right frequency. So it makes sense. If we have more photon, we shine more light, then the rate of absorption will be higher. Okay. Now in spectroscopy, there are a wide range of possible transition that may be investigated. Okay. Associated with this transition is the change in the shape of the molecule, or even transition of some of the much smaller components, such as and how do we induce this change? Okay, we want to induce this change. It depends on the type of radiation that we source is gamma ray or UV visible. Then we will have an electronic transition. Okay, from the blue line to another blue line. So this is the this is the electronic transition. And then if we shine it with the IR infrared, okay, and if we have our light source as a microwave, okay, they will induce a rotational transition. And we also, in case in NMR spectroscopy, we are using the radio wave, right, to induce a change in spin. Okay, so because this particle, atom, and molecule have occur at very different energies, and they can be considered as separate. It may assume that vibration and rotation can proceed independently of each other because the energy of the two motion are so different. And this is actually called a Born-Oppenheimer approximation. Here it is a table showing you the range of energy and time scale that this transition occurs. For electronic transition, the time scale is about 100 frames per second. Okay, and one order of magnitude lower is the infrared of magnitude lower, and then 3 order of magnitude lower than electronic is the rotation, and so on. Okay, so we have a different time scale correspond to different process occurring when they interact with light. Okay. Okay, to complete, sorry, before that, so it's a molecule rate 10 to the power of 2 times during the course of a single rotation. So it means that we can treat it independently. Okay, of course, to completely describe the energy level and its transition, we can set up a time-dependent Schrödinger equation, but yes, I don't want to show you the equation because it's quite long. So by having the approximation of Born-Oppenheimer, by partitioning the energy, we can treat it independently, and it actually simplify the theory. Okay, and talking about theory, again, I'm not going to show the equation or the Schrödinger equation, so it's not probably important for those who work in industry. But let us try to visualize the concept of quantization and the molecular energy level. Okay, we have electromagnetic wave, and electromagnetic wave is actually an oscillating electric field and magnetic. So the oscillating electric field will interact with the dipole moment in the matter. What is dipole moment? So it is defined as the sum of the product of the charges by the radius of this charge. And a molecule that has a permanent dipole moment, we call it as a polar molecule. And strong interaction means that the dipole moment must also oscillate, rotate or vibrate at the same frequency of the electromagnetic wave. So photon at that frequency is absorbed, causing the oscillation to be more intense. If there is no change in dipole moment, then this particular infrared region. So let's take a look at the example. Okay, for example, you have a homonuclear molecule like nitrogen gas or oxygen gas. So they have no net dipole moment. Okay, they are symmetry. They don't have any net dipole moment. Thus, we call them as a non-polar molecule. Okay, and they won't be vibrational spectra. Okay, so we call them as an infrared inactive. On the other hand, let's say if we have a heteronuclear diatomic or polyatomic molecule that have a dipole moment and it is changing as the displacement passes through the equilibrium position, thus they are infrared active, and we can measure their sort of a selection rule in terms of the infrared spectroscopy. So I believe some of you may have collected the spectrum using infrared or UV visible, and Ms. Chow already explained, show you some of the spectrum in her slide. So normally plot it in a graph of intensity or absorbance against the frequency of wave number. So upon absorption of electromagnetic wave by a molecule, we ask three questions, and they are the frequency of the absorption, okay, and the line intensity and the size of the spectral line. So for the first question, the frequency of the absorption can be read off the spectrum. So you have a monochromator and the detector. Basically, they record the frequency of the absorption, and then and the type of interaction depend on the value of the. In terms of the spectral line intensity, it is determined by three factors, which is the transition probability, population of state, which is the Boltzmann distribution that I told you about, and the concentration of sample or path length of the sample. So this equation, the Beer-Lambert law, is worked within a certain concentration. So from the Beer-Lambert law, the absorbance will be proportional to the concentration. And how about the spectral bandwidth? Okay, so which factor determine whether your peak, if you look at your peak here, which factor determine whether your peak will be fat or thin, will be wide or will it be broad or narrow? So there are three factors, and they are natural line width, Doppler broadening, and pressure broadening. I think I don't have time to discuss in more detail, so I will come back if we have enough time. So I will just keep this pressure broadening. I will go straight to the Ftir instrument. Okay, the Ftir instrument is for us to measure the vibrational state or transition of our molecule. By measuring this state, we actually use it to identify compound by looking functional group that are contained in the sample. Okay, so Ms. Chow previously has shown some of the spectrum. We can look at the presence of contaminant in our sample. Okay, so Ftir is really useful if you want to look at in terms of the functional group of our sample. And the term Fourier Transform. So do you know what is Fourier Transform? So Fourier is actually a mathematical process to convert the raw data into the actual spectrum. So the data we have from the instrument is actually a time domain spectrum, and we need to use a Fourier transform to convert it to a frequency domain spectrum. Okay. So this mathematical process, this Fourier transform, we need to have a certain experimental setup. Okay. So in this slide, I will explain to you roughly how the Fourier transform or the interferometer works. So first we have a light source. And then it goes to the first curved mirror to collimate the light, and it goes. This splitter is used to split the beam into two, and they are perpendicular. So one arm goes to fixed mirror, the other to a movable mirror. The movable mirror moves back and forth at a constant velocity. Okay, they have a kind of like a delay stage. Okay, to actually move this mirror at constant velocity. This velocity is timed according to the very precise laser. So we have a Lahini laser over here. Okay, it is also act as an internal wavelength calibration. So by knowing the speed of the movable mirror, we can actually we can plot. Okay, we can later plot our data as a power of radiation against the function of time. Okay, so the two beams are reflected from the mirror and recombined at the beam splitter. And patterns is created. And some of the wavelength recombine constructively and some destructively at the beam splitter. So this interference pattern is called an interferogram. And this interferogram then goes to the beam splitter, to the sample, and some energy is absorbed and some is transmitted. So upon leaving the sample compartment, the light is pressed into the detector. After that, your computer will record it and apply a Fourier transformation algorithm to convert the time domain to frequency domain. Okay. So after you apply a Fourier transform, this is the spectrum that you will get. So this is more meaningful spectrum. Over here, I show you an example of the IR spectrum of carbon dioxide. Okay, it's the simplest vibrational spectrum. So we can then assign the peak, to some motion, for instance, the asymmetric or the bending mode of CO2. And how to assign this? Usually we will refer to the, if you're a student in my class, usually we just give a kind of like a reference table, and then they assign, okay, this peak is belong to this type of vibrational mode. But if you work in industry, there will be a huge database for you to compare with. State that we have in their software, they have a database to actually the program will automatically tell you that, okay, this is belong to this functional group, this is a molecule, this kind of chemical structure, and so on. So so this is the way you and here is another example of IR spectrum of biological tissues. So you can see that it gets more complicated when we have many molecules with different modes. So we have amide, lipid ester, CH in lipids, C double bond ester, and so on. Okay. To give a last example of a recent publication, quite interesting, using ATR, FTIR. So they do a fast screening and primary diagnosis of COVID-19 by using FTIR spectroscopy. Okay, so from this they can actually identify which sample COVID-19 like. So they a bit complicated analysis called multivariate, and they report that it can provide a chemical fingerprint for the identification of COVID-19 sample. So it is quite useful in the current pandemic, and I think there are also few other scientists doing the same experimental technique. You can Google search it, and I'm sure you will find it. Okay. All right. So I think I finished with the first part of my talk, which is on the FTIR, the vibrational spectroscopy. Now let's go to the second type of spectroscopy, we call the electronic spectroscopy. You need to know is that they are different in terms of the wavelength of the light source. Okay, the light source is we supply it not with the IR, but we use a UV visible. Okay, so Usually the UV visible, we record it from 200 nanometers up to 780 nanometers. So it is higher in energy, and thus the energy gap between the ground excited state will also be higher, because the y-axis here is the energy. And from the schematic diagram depicted here, you can see that the separation of energy between the vibrational, transition, and electronic. So the vibrational is very small, but the electronic is much bigger in terms of the energy. And let's more complete picture of electronic transition. So electronic transition seems more complicated because there are so many possibilities of transition. Okay, let me start by explaining to you the absorption process. Again, without any light, so where do we expect our molecule will be? So mostly it will be in the ground state, or we label it as S0 state. Okay, so most of the molecule without light, it will be here. And then the many line you see here is actually the vibrational line. Okay, so there is a vibrational state in between the electronic state. Okay, it exists in S1, it also exists in S2. Okay, but not necessarily there are same number of state and the size of this energy gap. So if our molecule absorb light, it can go to any state that I label here. It can go to S1, it can go to S2, and so on. So we have many different state of electronic. Okay, and okay, let's say it goes to S2. Okay, and as I said earlier, it will not stay in the excited state forever. It will decay naturally or spontaneously. But we want to understand how it's going to decay, how it's going to relax. Okay, in most of chromophore molecule, it will follow the following pathway. First, it will decay to the S1 by the process we call as internal conversion. Okay, and subsequently it will relax to the lowest from S2, it will relax to the lowest vibrational state of S1. And then by a process called vibrational relaxation. And these two processes, internal conversion and vibrational relaxation, they are radiationless decay. So radiationless decay meaning that there is no light will be emitted, and the molecule will just lose its energy by heat through collision. When it goes to S1, the lowest state over here, it decays back to S0 by emitting the so-called fluorescence. Okay, so it will only emit fluorescence from the lowest another possibility is that from S1 state, it can also go to another state we call as triplet state by the mechanism of intersystem crossing. So the difference between this S1 and T1 is actually in terms of the speed. Okay, again, to talk about this, we need to understand more of the theory of quantum mechanics. But I will go straight away to the experimental setup. Okay, so how do we want to measure the absorption and emission of light, okay, by our molecule or sample? For absorption, we need to use an instrument called UV visible spectrophotometer. Okay, here is the setup, and we have a light source over here, and we have a monochromator, which basically to select the wavelength that we want to measure. Okay, monochromator basically only allow a certain wavelength passes through the sample. Okay, it's actually to have a double beam spectrophotometer. Spectrometer, it basically divide the light by two arms. So we have a beam splitter over here. Okay, and then one arm goes to sample cell and another goes to the empty cuvette. Okay, then you take the logarithmic of I over I to get the absorbent. And how about the emission? Okay, how do we want to measure this emission of fluorescence over here? So the emission, we use an instrument called spectrophlorometer, and you have a source over here. Molecule with a white light, we only want to excite our molecule at a specific wavelength, and then it goes to the sample. Okay, so we have and then emission monochromator, and then we have the detector. All right, the things a bit different compare of absorption arrangement, because you don't want your excitation light to go to the sample, but instead you want to measure only the fluorescent. Okay, so the fluorescent emit in all directions. Then we have another monochromator just to select a wavelength that goes to detector. All right. So this is the example of chlorophyll A. It is a pigment in plant, right? So that give a color to plants. And the function of chlorophyll A is to absorb light from sun and use it for photosynthesis, or we call it as a light to chemical energy conversion. So if we measure the spectrum of chlorophyll in a plant and extract out the chlorophyll A, so this is the spectrum that you will get. Okay, you can see very clearly that the chlorophyll absorbed mostly at the right side of the spectrum, and also at the ultraviolet region. And there is a very less absorption at the around 500, which is a green color. So that's why you see your plant or your chlorophyll as a green color, because it's just transparent to this color. Okay. All right. Now I would like to explain on the emission spectroscopy, or we call it as the luminescent. So luminescent defined as emission of photons from. Basically, there are two types of luminescent relaxation from singlet excited state, S1 to S0, and there is relaxation from triplet state to singlet state. So this is how radiation being emitted after it is being excited. Emission, or the excited state, the Kasha's rule. So the Kasha's rule said that for organic molecule in condensed media, the emitting level of a given multiplicity is the lowest excited state of that multiplicity. Means that, in a simpler word, it means that if we excite our molecule at higher excited state, S2 or S3 of the electronic element, the fluorescent state of S1. Okay, so we call it as fluorescent. So the emissive rate is in the order of fluorescent, whereas from the triplet state, okay, is called a phosphorescent. And because the phosphorescent is a spin forbidden transition arises due to a change in spin, or we call it spin flip, so their emission rate is low, which is in the order of millisecond to second hour. And this is an example of spectrum. Okay, in this image here is if you look at the red line color, it is actually the emission spectrum. The blue is the absorption. So you can see that the absorption and the emission looks give a rule. It happens when the vibrational level in the excited state and the ground state is similar. Okay, it's not necessarily true for all molecules. So some molecules, they have a very different vibrational state between S1 and S0. Okay, so they will not have this mirror image. Okay, so in this case of mirror image, the absorption spectrum reflects the vibrational level of the electronically excited state, and the emission, the vibrational level of the electronic ground state. Okay, I think this will be the last part of my talk. Okay, which is on the ultrafast laser spectroscopy. Let me start this topic by sharing with you 1978. So at that time, there was a public controversy whether when the horse galloped, all the four legs came off of the ground. Okay, there is no fast camera around that time. So they hired a person named Edward Muybridge to solve and prove that, you know, the four legs is actually came off the ground. So you take a look at the image here. Yeah, so he designed a racetrack in California, in Palo Alto, where he put a horizontal line along the track. So the line are attached to a battery kinetic camera. So whenever the horse crosses the line, then the camera will automatically take the snapshot of the horse. So by this image, prove that it is true that the horse was flying for a short moment. So this possibly is the first image showing the use of photography to stop time and see things that humans. So this is in 1878. But how about now? What do you think? How short or how fast that we can capture an image? So after almost 150 years, and we want to know, you know, as a scientist, you know, how fast we can. So this is sort of the summary of the journey of time resolution. So we have actually improved from measuring second in the 1800, you know, from measuring second to millisecond, and then we can measure nanosecond. And when the pulse laser was, we can go to femtosecond, which is femtosecond is 10 to the power of -15. And now people have started to measure attosecond. So attosecond is 10 to the power of -18. And you might be wondering, you know, why we are concerned so much with the time resolution. So let me tell you why. Chemists or physicists or biologists, we have learned this diagram before as a student. You know, let's say we have an initial reactant of A and B. Okay, let's say this is A and B, and then it will turn into a final product. But as a student, we were taught that there is a transition state. Okay, it's actually a black box. We don't know what is the transition state. We put a question mark, or we hypothesize the mechanism. And it is usually hard to observe this black box because it occurs at an extremely fast time scale. So from a fundamental point of view, it is indeed very important to uncover this black box, because then we can understand why the reaction proceeds to form product in a certain way. So by using the technique called ultrafast laser spectroscopy, we can actually track the reaction pathway. Okay, something like we freeze them on time, we take them frame by frame, and we do a slow motion pictures. And you can think of it about the, like, for example, pharmaceutical industry or catalysis reaction or enzymatic reaction, and so many other chemical reactions that we don't fully understand why the product yield in a certain ways. And so by using this technique, we can actually determine what are things that in. So this is the setup to create a super fast, or we call it an ultra fast camera. We use a technique called pump probe, or in other words, it's a transient absorption spectroscopy. I'm not going to bore you with more detail of the experimental setup, but the important thing here is that in order for us to do this experiment, we need to use what's called is a pulse laser. So pulse laser, which is very, very short. Okay, this is called a femtosecond pulse. And this ultra short pulse is basically million times powerful than a normal light. Okay, it's a million times powerful. Even your laser pointer, and we really need to be careful of handling this laser, or it can actually really burn your eyes and damaging. This is the femtosecond that I told you about. Okay, we are using the chirp pulse amplification laser. We call it as a CPA laser, which generate around 80 to 90 femtosecond pulse at 800 nanometer, so almost close to the IR region, and it emits 4 watt of power. So it is pretty strong, if for example you saw surface, it can generate heat up to 30,000 Kelvin. Okay, and this is another setup called OPA, Optical Parametric Amplification, where the 800 laser that I showed you before, we can actually use this setup to tune the laser from 240 to 2000 meters. So basically from UV to mid IR. And this is basically the setup. So a lot of optics involved, okay, to actually make up the ultra-fast camera. And I mean, it is not cheap also. We are basically, the laser is in right now, and we are actually building the setup currently. Okay. All right. So I just before I end, I just want to share with you some of the application of ultrafast in. Okay. So one application is the mechanism of bond breaking of cyclobutane. Okay, cyclobutane, we have a kind of like a ring, square molecule over here to form 2-ethylene. Okay, so before the ultrafast was invented, there are two proposed mechanisms. Either the reaction it just break simultaneously, or they have a molecule break, one bond break one at a time. You know, so in this case, they will form a molecule called tetramethylene as an intermediate. Okay, so of ultrafast, they wouldn't know how the mechanism of this bond breaking, and by using ultrafast, it was shown that was formed with a lifetime of 700 femtosecond. So this is the correct mechanism of cyclobutane bond breaking. Okay. The last example, okay, and also my final slide, okay, is I would like to share with you discovery of ultrafast phenomena even in our eyes. So our eyes is made of so many different components. They are essential, and once the light reach to our lens, so it will focus the image on the retina, and there are cells in our retina that respond to send signals. So the cell here is called rhodopsin, and it has a molecule called, and it responds to light by twisting around a single bond in about 200 femtosecond. Okay, so this is basically the first step in our vision. You know, if we don't have an ultrafast technique to measure this, we wouldn't know that the cis-trans conversion is important for us to be able to see image. Okay, so I think that's all from me. Okay, and thank you very much. And I give back to Lawrence. Right.
Okay, thank you, Dr. Faisal. We had a little trouble with your presentation. Sometimes the line went off. Sometimes, not all the time, but every time. So I couldn't interrupt you because I think it's your network issue.
Oh, okay. Sorry.
Okay, anyway, ladies and gentlemen, before we move on to the question and answer session, I would like to ask each and everyone to please switch on your camera for a while. I would like to take a group photo before you proceed. Everybody, can you please switch on your camera? We can have a group photo. See so many beautiful people today. Very good. Beautiful day indeed. Okay, I guess that's the people that want to come on camera. Others maybe they're a little bit shy, so I'll ask our camera person is also on standby to take the photo. On the count of 3. 1, 2, 3. One more. 1, 2, 3. Okay, great. Let's move on to the question and answer session. You can leave your camera on if you want to. Any questions from the floor? I saw someone just now was raising his hand, then he put it down.
Assalamu alaikum.
Yes, go ahead, sir.
Assalamu alaikum.
Please mention where you're from and who you like the address the question to.
I want to ask the question about the IR. So I saw recently this presentation. Prof, there are two questions I wanted to ask. One is that how do you convert the data? I mean, the one that they give you normally is inverted graph. So if you want to change it, the other graph that you have shown, how can we do this, Prof?
Okay, you are talking about absorbent and if infrared, they usually have I mean sometimes they report it as a transmitted.
Yes, Prof. Yes, you're right.
And absorbent is basically just absorbent is basically negative log of transmitted. You just apply a negative log to transmitted.
Oh, thank you.
Yeah, that's all.
And second question is that can you share the table that you are giving the to the students? Can you share this table with us?
Oh, sure. It's actually available online. I got it from Google Image from Thermo Fisher.
Okay. Thermo Fisher, right?
Yeah. You can actually get it online. Just search about a characteristic table of IR or functional group of IR. Then you will get a lot of table.
And last thing is about the contaminants because I work normally with activated carbon, Prof. So you mentioned a very good point about the contaminants, which is very important in case of biochar or char, which is not always pure. So how do you actually target your contaminants? Because for me, sometimes if you know this water or you are sure what type of contaminants are there, but if you have a biochar, you don't know sometimes which contaminants are there. So it will be very difficult to search it in the whole, library or do a understanding of the graph. So what is your advice in that case?
Yeah, so I'm not your research, but what my opinion is that you always need to have a kind of like a standard, without any contaminant, a reference for you to compare with, like what Ms. Chow was showing. If you need to have two spectra overlapping, and when you see something like a new peak in the infrared spectra, then you start to interpret it as new things or contaminants in your sample. So my advice is to actually have a standard spectrum, okay, or reference spectrum.
Okay.
That you want to compare with, then you can identify what.
Oh, I can't hear you.
You lost me again.
Yes. Okay, my name is Firdaus. Thank you. I'm from UPM. So thank you for your answers. Is it possible you can share your email ID if I want to ask further questions?
Okay, sure. I will write down my email in chatting.
Oh, yeah. Thank you, sir. Thank you very much.
Let's open the floor for more questions. Anyone else? You can raise your hand. The icon right at the top, or you can type your questions as well. Any questions? Yeah, there's someone I think you want to ask a question. Go ahead. Please ask your question. No more questions. Okay, I give another 30 seconds. If there's no questions, we will end our session. Any questions from anyone? You can either type in the chat, or you want to ask directly, you can also use your mic to ask question. Okay, that's a question. Hi, doctor. I would like to know if.
Okay, let me try to read it.
From Jia Min Fung. Hi, doctor. Would like to know if the spectrum obtained is too weak, the 1% T, can we use it for matching?
I mean, it depends on how weak is too weak. You know, if you talk about weak to an extent of the noise, you know, when we talk about spectrum, we have a signal to noise ratio. If the signal is at the noise level, then I would say it is very hard for us to correctly determine that the functional group is exists, and it's hard to convince people that the exists. So I would say I would say try your best to improve it in whatever way that you can, you know, in terms of the signal. So as long as it's higher much order than the noise level, then it is fine, I think. Yeah.
Okay, next question is from Encik Muhammad Faris. Over to you, sir. Encik Muhammad Faris.
Hello, yes. Can you hear me?
Go ahead. Please ask your question.
All right. My question to Dr. Faisal. Is there currently, because we know that ultrafast laser has very good properties in detecting materials, chemical properties. So, sorry, firstly, my name is Muhammad Faris. I'm from UITM, Electrical Engineering. So I would like to know, is there any laser type that is compact enough that we can bring it mobile, take it out on the street or field, so that we can do spectroscopy on site and get the result in real time? Is there any on the market? Thank you.
All right. Thank you very much for the question, Jeffrey. So basically, there are many types of laser. Okay, they are usually we divide it into continuous lasers and pulse laser. Okay, so continuous laser is something similar like your laser pointer. Okay, pulse laser basically it emits like a burst of photon, right? A burst of light. So it doesn't emit continuously. For continuous laser, I wouldn't say. I think it is not really. It is common to have it portable, okay, because of the simplicity of the but if you talk about pulse laser, then it become a bit more complicated. But I believe in the commercial, there are pulse laser that are portable, but they are in nanosecond pulse duration or per second. So they are not in a femtosecond time resolution. So if we want to measure something on site, so we can still use nanosecond or picosecond laser. I think it is quite strong enough for some experiment, for instance, laser-induced breakdown spectroscopy. So there is a technique. So what you do with this technique, you can shine in laser into your sample or into a surface, and it will emit a plasma. So you can characterize. You can do an elemental characterization using this technique. But for example, if you want to do ultrafast spectroscopy, like the one that I mentioned, you can see how big is the instrument, you know. And this the technique of generating this femtosecond pulse is actually developed by a scientist named Donna Strickland. She got a Nobel Prize in 2019, and the setup. I mean, as far as I know, there is no. It's not easy to make it into a portable. You know, it is a very sensitive instrument. You need to have a temperature fluctuation of plus minus 0.5. You need to have a stable air. Humidity, so they are very sensitive instrument for now, but I am hoping that in the future there are more modern laser, you know, more laser that is you know, outside the field.
Okay, right, good. But As per my question, can we have the result in real time, or do we have to do post processing on the data first before we can determine the spectroscopy results?
Yeah, definitely. If you measure something, you will get a raw data, and what normally people do, you will process it. Okay, you have a post processing. Either you develop your own statistical, or you have your own program to analyze the data. So usually you will get raw data, and you need to decide how do you want to process it into whatever information that is useful for you. Okay.
Okay, there's another question here, and the question is there a way to amplify the region of interest in IR?
Maybe I want to add on with what Dr. Faisal comment about the IR software, because I'm from instrument company. So normally, I would say I understand quite well about how the software works. So like example, if you want to convert from absorbance, okay, to transmittance, actually in the software, there is a button to click. You just convert it, then it will auto change for you. Even though your spectrum, maybe certain people prefer to look at this way, or if you want, you can do it this way as well. Okay, so, and of course, if you want to look at certain range, I see there's a question here. So normally we scan from 400 to 4,000. So after you scan, maybe you just want to look at example 2,000 to 4,000, that range. Okay, so actually you can go and zoom in or draw a box, or you can go to the spectrum property to identify that is the range that I want to look in. So for identification, the instrument normally also come with certain standard of library. So after you scan your spectrum, okay, you can go to the library and say that you want to search against this 5-peak example at different Baxi X here. So it will auto search for you, and then it will tell you and identify for you. So in the library search, actually there is a number, the index number. So like example, the perfect matching is 1. So if you get 0.98, that means it's a good match. But if you get 0.55, that means it's a lousy match. So all these actually, the software can help you to do all this. Even though the identification, so you have 5-peak example. So this peak maybe fall at Baxi X with 2,900. So you can use your cursor, go to 2,900, that peak, that location, you click on it, then it will tell you, okay, this peak belongs to alkane group at 2,900 is a CH stretching, so it belongs to SP1 or SP2. So all this is within the software capability. But of course, as a student, okay, like what Dr. Faisal as education, normally old day when I'm a student, I have to remember it because this is the exam question, right? So they will give you a molecular structure and then they will give you score. Okay, this is what. But with today's industry, I believe nobody will remember it unless people like us, we always deal with it. The software capability, even though you don't know to do this. But of course, after the matching, everything, the customer still have to have the knowledge, what is the sample material. Okay, so that is my comment. Yeah.
Okay, we have another question for you, Ms. Mei Ling. It's from Mostis BHV. The question is, has your handheld FTIR been tested for crime scene investigation? For example, at vehicle accident scene, there will be many pieces of vehicles scattered at the site. This handheld device could be useful for the CSI team to identify these parts, which will be crucial for collision simulation.
I have this slide type of presentation about the question you asked. If you are interested, you can let me know. But I just briefly explain here. Yeah, just now, if you still remember the picture, it's a blue color handheld, right? So we have some investigation study, but not in Malaysia, in overseas. So like example, you have two cars, okay? So you have a Honda, you have a Proton Saga. So both of them crash. So there are the paint from this car, of course, will go to this car, right? So this car paint also will go to this car. So basically, you can use the handheld on the spot, whereby no change of the condition. We emphasize on that. Because when you take out the paint from this car, okay, it might be different with the condition of this car. So on the spot, we scan as the paint as it is, and then we get the spectrum and say that, okay, this paint actually is from this car. Okay, because there's a lot of cases, maybe this car sudah lari, okay, and then replaced by another car, okay, and say that go to court when they do the analysis, this paint is not belong to here. So that means actually it's no case. Okay, there are people who do this study also. I think we sell a few units to police in Singapore, but not in Malaysia. They have this investigation because different paint manufacturing, actually they come with a different FTIR spectrum. That there is a unique or marker on their paint. Okay, it's just like if you buy a Ferrari red, so the red is different with your Proton Saga punya red. Okay, that is some we call it expensive and cheap paint. Okay, so that is the different. But we do have people who study this, especially in the crime scene. Okay, whereby you want to remain the condition as it is, because when you spoil the condition, then it will be no case. Okay, we want to preserve. Yeah.
Thank you, Ms. Mei Ling. Next question for Doctor. Do you use molecular computer stimulation such as Gromacs before conducting the physical experiment to identify the real-time mechanism of the reactions?
Is it me or Doctor?
Doctor, you say doctor, so
Okay. So to be honest, I'm not using. I mean, there is another group that doing a computer simulation, because doing computer simulation require another set of knowledge, another set of experience. So usually, in chemistry department, we will collaborate with those who are doing computer simulation. Okay, so to complement our experimental results. Okay. So my answer is that I didn't do it personally, but I usually work with other researchers. Thank you.
Okay, thank you, Dr. Faisal. Next question for Ms. Mei Ling is less than 0.5 matching on SP library matching considered good, quantitatively matched, or must be 0.98?
It depends. That's why I emphasize that people who do the library research, they should know what they want and what is their sample. So you cannot send me a sample, okay, and tell me, oh, it's unknown. It's very difficult because the peak, how they do the matching, basically is like you have 5 peaks here, so the library will match like this, okay? So if all of a sudden one of your peak, okay, is like this, you got this extra at different locations. So then we will say maybe this is different with the original. So maybe this one is a contaminant from the sample itself. Okay, so if you look at here, the peak position here is always fixed. Like example, if you have a CH at 2009, okay, it's always there. But in the world, there are a lot of samples also have this peak. Okay, so when you do a peak match, so you must have an idea. So it doesn't mean that the highest is the perfect. Okay, the lowest is not good. So in the software, they also will give you a guideline. So who else got this peak? they will give you a guideline, a hint, so that you can look for the answer. So of course, FTIR is not a absolute method. Okay, because a lot of people think, oh, once I do the library match, I get this answer, then it must be this one. But sometimes it's not. Okay, but of course, we always say that if the good match, then it will belong here. But when you look into detail, maybe over here, there is some small peak that is not exactly matched. So that is one thing that you have to consider as well. Okay, so beside the normal software, basically, a lot of customers also look into chemometrics. So you can use the spectra after you collect a lot. So a lot here means that not 5 or 10, we are talking about maybe 100, 200. And then you do a correlation. Like example, you want to do a correlation with TGA, ESC, or some other analytical method. So then you can have this chemometrics software to help you to do this statistical analysis as well. Okay.
Okay, thank you. Thank you, Ms. Mei-Ling. One question for Dr. Jasmine. Ms. Mei-Ling did mention about samples. So if people have samples in Penang or Johor and they want it to be brought to MIMOS, how do they do that? Doctor, would you know? Would you be able to comment on that?
Yes, sure. Okay, for the time being, due to this pandemic, we don't encourage you to actually walk in. Okay, so we would encourage you to actually post. You can post a sample to us and then inform us, and then once give us the tracking number. So once we receive the sample, we will inform you, and then we will carry out the analysis. But at the same time, you can inform us what are your expected results or what are you looking at, and then so that we can actually, work accordingly. Yep.
Okay, thank you, Dr. Jasmine. Any more questions from the floor?
Jasmine, Dr. Jasmine, can you please share the address details, contact details?
Right, sure, no problem. I'll just type it out here, right?
And do you have any kind of a price list for all the analysis?
Yes, sure. So you can drop us an email. I think Lawrence has shared the email address. Never mind, I'll share it again. And then you can drop us an email and we will provide you the quotation based on what are you expecting. And then from there on, you can decide whether you want, you can post your sample to us.
Okay, please share your email, ma'am.
Yes, sure.
Thank you.
Thank you.
Okay, let's see. We have, okay, there's 2 raised hand, is it? Okay. J. Ahmad, over to you, sir. Ahmad Basir. Go ahead. J. Basir? Or is he ordering lunch for all of us? I'm not sure. Okay, J. Basir, so we will. Is he on? Or maybe accidentally raised his hand. Okay, any other question? Or you just want to share? Okay.
No more questions.
Okay, thank you, sir. Okay, we'll have another minute before we wind down our event for today. Dr. Jess just put her email on the chat, so please copy it and use it.
Where from can we find the details of chemometric software, which she mentioned about the lady of the company? She talked about the chemometric software. Where can we find the details about it? Could you please pass my question to her?
Normally, whoever supplier who sell the FTIR, they can sell you the chemometric software also. But the example, if you buy the instrument from Agilent, okay,
yes,
we can sell you the chemometric software together as a bundle package with
yes,
the instrument. Yeah, but this chemometric software normally is not from It's not made by our own Agilent people. It's not Agilent product. So we will get from third party. So same thing happened with other supplier also. So most of the supplier, they do not have their own. So if you do a search, you can get it from Know It All, ST Japan, Grams, all these company, there are software companies, software and library company. So even though like today, if you want to get a polymer library from me, so Agilent don't have polymer library. I also buy from ST Japan and then put inside my instrument and sell to you because we are instrument company. We are not software library.
Yeah, I understand. Prof, are you using this software in your lab?
No, I'm not using it. Yeah.
Okay. Thank you, Prof. Thank you very much. Thank you, ma'am. Thank you for your time.
Okay, great. Thank you, everyone. We appreciate you being here. Big thank you to Ms. Mei Ling, Dr. Faisal, and Dr. Jasbin for sharing their knowledge with us today. And once again, if you want to see or if you want to learn more, don't forget to follow our social media sites, MIMOS Malaysia, in Facebook, Twitter, or YouTube for more information and also for the upcoming webinars. Once again, thank you. Stay safe and have a productive day ahead. Thank you, everyone. Bye-bye.